In that last problem that we just did, we saw that having two infinite sheets of current would create a confined region of magnetic field. Now, two sheets of infinite current is a little impractical. However, if those sheets, instead of being infinitely long, were wrapped around in a cylinder, and we could make the current continue to flow in a circle, we would have a similar situation. In fact, by an application of Ampere's law to this Amperian loop right here, we actually get the exact same results. The total current in here is equal to lambda times h. This top region does not have a magnetic field because it's canceled by the magnetic field created by this segment. And so the magnetic field is still mu sub naught lambda. Now this does lead to difficulty. If we have this cylinder, how do we get the current to flow around it? So let's modify it slightly. Instead of a sheet of metal that's been bent into a cylinder, what if we took a single wire and wrapped it many, many, many times so that it appeared as a cylinder? In that case, we could force current to flow through the wire, and it must flow through each coil of the wire, and therefore we would have something approaching an infinite sheet of wire. Now, when solving that last problem, I alluded to capacitors, and that's because what I've been describing, is a device called a solenoid, or in circuits term, an inductor. Now, the difference between a solenoid and this infinite sheet is, again, it's made of a bunch of wires, which means that instead of having a linear current density, it does have a single value of current through that wire. But we can say that the current density is equal to the current in a single wire, I, times the number density of the wires, N divided by L. So for instance, if a single wire carried 1 ampere of current, and we were able to loop 1,000 of those wires in 1 linear meter, then 1 meter of this sheet of wires would have 10 amperes of current. So we could say it has a current density of, I said 10 amperes, I meant 1,000 amperes, 1,000 amperes per meter. Sometimes you will see it written as I times little n. Big N represents the total number of coils divided by the length. Little n represents the coil density, which is sometimes easier to find. Put it all together, and we can say that the magnetic field inside of a solenoid is equal to mu sub naught I times N over L, or mu sub naught I times little n. Now, another configuration that you often see, because if you have just one wire wrapped in a single cylinder, you have wire starting at this end and ending at this end, which does sometimes present logistical problems for a circuit element. However, if you take that cylinder and then wrap it back around on itself, the shape you get is a torus, and in a real solenoid, you would have the input wire come in right here, and the output wire come out right next to it. But for our analysis, that doesn't matter, because we can look at the magnetic field inside the torus and see that our Amperian loop, no matter where we are in this torus, encloses one bit of current for every loop that the wire makes. So we can still use B equals mu sub naught I times N over L, only this time the length of wire, or the length of this part, is equal to 2 times pi times r. So a toroidal inductor has a magnetic field inside of it mu sub naught I times n over 2 pi r.